Particle physics. The best way to sound sophisticated and smart no matter the scenario. But do you know what it is or does? Probably not, and neither do I, quite frankly. You're probably like me, who looks at complicated diagrams, acts like he knows what they mean, then you try and look at it further, only to be like, But there's one theory connected to particle physics which is much easier to explain, that being the theory of supersymmetry. No, I'm not talking about you for once. You put stone in your commutators for some reason. Anyways, over the course of the next few minutes, I'll explain to you what exactly this fancy theory is, how exactly the science surrounding this stuff works, and why it is so important to modern science. Before I go insane trying to explain this concept, I want to take a second and say that I am not an expert on this kind of stuff. I am merely a nerd who finds absurdly complicated parts of science fascinating, like why argon is in the air or why people think GregTech is hard. It's really not. But anyways, to get started, we need to look at this diagram. Oh wait, that's not Minecrafty enough. Much better. This is the standard model. It's a model which shows every particle which makes up everything you know and love. It is split into two sections. The quarks and leptons, which are these piggies, are made up of fermions. Fermions are characterized as having a half-integer spin. What does that mean, you may ask? Quite frankly, I don't know. They're way too confusing for me to understand. But what I do know is that these spins play a major role in how these particles interact. Also, I should add that fermions are the only particles which have mass. Now, a key detail about fermions is their disgust for being smushed together. Due to the Pauli exclusion principle, fermions will change form when in the same quantum space as other fermions. Think of this principle as a group of cows in this 1x1 hole. This group of fermions, which is known as fermionic gas, are smushed together, taking up the same quantum space. Due to the exclusion principle, aka entity cramming, the cows will change their state from living cows spinning clockwise, like Maxwell the cat, into a piece of beef on the floor spinning counterclockwise, thereby allowing both to take up the same quantum space. But you want to know something that doesn't follow Pauli's silly principle? That something is bosons, particles with a whole integer spin. These make up what we would consider energies or forces in nature. Bosons are what make electromagnetic energies, light, and literally hold all atoms together. Unlike fermions, there's much less of these things. There are photons, which act like God and give us light. There are gluons, which are strong nuclear forces. These forces keep quarks connected to one another in order to form protons and neutrons. This relationship is known as quantum chromodynamics, which deserves its own video entirely. Think of gluons as a lead between two rabbits. They keep those two together no matter what. Anyways, then come W and Z bosons, which are considered weak nuclear forces. They're what's keeping protons and neutrons together inside an atom's nucleus. That's the basic rundown of every boson there is. I'm totally not forgetting one. And lastly, we have Higgs bosons. This is a weird one. If all the other elementary particles were naturally spawning sheep, the Higgs boson is like the pink sheep of the group. The actual boson isn't too important, as it quickly decays into other particles. Its actual importance is that it represents the Higgs field, which occurs everywhere in the universe and is responsible for quote-unquote creating mass out of particles of a given energy level. The type of elementary particle created depends on the strength of the particle itself. So now that we know the standard model, we can finally look at some of the problems it has, besides the graviton, which is actually starting to annoy me because but anyways, to quickly and simply go over some issues, the model doesn't explain why gravity exists, even though it's a fundamental force of everything. Secondly, it doesn't give reason for dark matter and dark energy's existence, even though they make up 80% of the universe's mass and energy. To explain, dark matter is a type of particle which can interact with normal matter, but can't interact with any forces besides gravity. It's also theorized that dark matter attracts normal matter together, which in turn allows for entire galaxies to materialize. So it's kind of muy importante por la física de partículas pero no sé. Lastly for this section, the model doesn't explain the discrepancy between the gravitational scale and the electroweak scale, both vital in particle physics. These two scales are known as a hierarchy for some reason. After all of this, I can finally explain how to fix these glaring issues. Here's where I can finally discuss supersymmetry to you science-loving crowd. Supersymmetry, or as I'm going to refer to it as, SuSy, is the idea that for every particle on the standard model, there is a supersymmetric particle of it. What does that mean? Well, say for instance we have an villager being a type of fermion. Now we have an illager, which would then be his supersymmetric particle, being a boson. This idea can be switched. Bosons also have fermions as their super partners, while they themselves only interact weakly with one another. As a whole, a few notable facts can be theorized for these partner particles. Hey guys, Editing Dewey here. While editing, I realized that the facts about SuSy particles in the next section were actually wrong and wildly generalized, so I didn't want to accidentally spread misinformation like a Twitter user. So here's the best info about these particles as I could find. Firstly, these particles have varying masses based on the base particle. However, a key trend in these SuSy particles is that they are normally much heavier than their normal counterparts, being around the size of an up quark. Secondly, the interaction between the normal and the SuSy particle is largely dependent on the particle itself. For examples, gluons and gluinos, their SuSy partner, would interact strongly with one another since it's a theoretical large mass interacting with a strong nuclear force. Lastly, the electrostatic properties of the particles would also vary from superpartner to superpartner. They would also likely decay quickly compared to normal particles. These are the most realistic findings I could find. Back to your normally scripted nerdy Dewey video. So now we know the basics of how SuSy works, we can finally use that theory to explain how we can solve those pesky problems plaguing the problematic standard model of particle physics. That's a lot of P's. Firstly, gravity. This pest is solved by the idea of supergravity, which is something that needs its own video as well. In the best way I can put it, if the gravitino exists, then the graviton must exist. It seems like a no-duh kind of answer, but this is a rabbit hole in and of itself, and somehow it includes move on to dark matter and energy, which the supersymmetric particles would take that form as dark matter and energy, as they may be a reason as to why we can't regularly observe it formally, and why some dark matter still quote-unquote lingers, even after 13.8 billion years. There has been steady progress to solve this headache at CERN's Large Hadron Collider, which is the best way to study new particles on Earth. The LHC basically makes two hadrons, or particles made of quarks or antiquarks and gluons, headbutt one another at near light speeds to create possible new particles to be studied. Imagine two minecarts with pigs inside them collide to form a boat and chicken. That's kind of the concept of the Large Hadron Collider. Lastly, for the hierarchy issue, SuSy would give Higgs bosons, which allow for the electroweak scale's existence, new types which have the capability to have differing strengths and thus could possibly connect the gravitational scale and the electroweak scale. This would more substantially connect gravity to weak nuclear forces and electromagnetic forces, allowing for gravity to more easily fit into the model. And that's the most basic way I could possibly explain particle physics and supersymmetry while not going insane. This was more of a lecture than entertaining, and I apologize for that, but it's something I wanted to talk about ever since I started playing Supersymmetry, the Minecraft mod pack. This video has taken a lot of my sanity with it. I, no joke, have probably spent over 4 hours just reading articles and taking notes for this video, which is very uncommon for me. Now I ask you, my viewers, was this video insightful? Did I explain the concepts the best? All constructive criticism is welcome. If I missed anything or something wasn't entirely truthful, just scream at me in the comments over it. I really don't mind. Anyways, I hope the collection of quarks and gluons watching this video right now has a good rest of its day. Bye guys.